Heck yeah. We're trying to eat. Yeah. I guess we'll just wait for a couple more people to kind of stroll back in the room. Maybe we'll be able to trim off the first few seconds of recording. Help yourself to some pizza, courtesy of Hello World. The name, I mean, how do you go about getting the name Hello World?
He just recently changed it. It's called
E-Prize.
And I've heard of that, but oh well.
I would expect the Hello World to be like a software console. Yeah. And so
They're promoters, right? They instead of bad campaigns, that type of campaign, right?
I think so, but I'm guessing it's true. New media ad campaigns or online ad campaigns mostly? No. Hectic. Pretty cool. I saw lots of BeagleBones in use. I saw a one that would print circuit boards. So it's using ink. So it's not like Squink also uses BeagleBone Black. So Squink uses conductive ink, and it'll print on all sorts of materials and make conductive things. And it uses, instead of soldering, it uses a paste, a conductive epoxy, in order to attach the devices to the circuit. So you can. Well, it's not using the epoxy for traces. It's using a conductive ink for the traces. And so it builds up. It looks kind of like glue-ish-like. So it builds up these traces out of whatever their conductive thing, and then it uses a different epoxy in order to glue the devices down, conduct them down to the to whatever they've drawn on.
Were they just using a regular print head, like the inkjet print head?
No,
Their own tool?
their own heads. Wow. Okay. Hello. Oh, that's that phone. Okay. So that thing is pretty cool.
Wow.
Justin.
Great.
But Squink was like, it's pretty cool. But then I saw a couple of other things that made me think that there's cooler stuff coming pretty quickly. Because Squink is pretty cool because it prints on all sorts of different materials because of the way it's doing it. But then I saw somebody laying down copper traces. So they've got a customized print head. You're also using a BeagleBone Black for their control. Yeah, they were laying down copper, so they were getting like conductivity that's like, and they were doing it on FR4, so like the same thing that standard PCBs are made out of. And so they were making pretty decent quality, printing pretty decent quality PCBs. So I thought that was pretty cool. And then I saw what they call that pick and paste.
Yeah.
So it's a pick and place machine, but it also puts down globs of solder paste.
Yeah, that's
Oh, okay. Cool. I was super impressed with that one. I met the guy that was one of the partners that started that up at the Machine Kit meetup in Madison, Wisconsin. Of course, I didn't know that his project was based on BeagleBone Black. I just knew that he was working on Machine Kit, and it's actually got vision on it too. So it's got a little camera on it, and it actually will line up the board. Like you just throw the board down, and you still have to kind of make it level, like so. That's just laying a board on a plane. It'll automatically figure out the orientation by using the camera to figure out looking at fiducial marks on the board. and will rotate the parts in order to place it on there correctly. I was pretty impressed with that. It doesn't like read from, it doesn't take standard tape and reel, so it just works off of tape instead of the reels. But for doing a small number of boards, I mean, the combination of those two, like print your own PCB and then do pick and paste, you know, you can, yeah, you just, the only thing extra you need is a toaster oven and you're done. So now we could do the 603s, the pick and paste. But getting away from that entirely, I also saw there was a coffee machine that was done with the BeagleBone Black, the Pour Steady, and they were actually making like 6 cups at once, but they were using a pour head that would just pour the hot water all across the grinds. You get a smooth flow. You know, made good coffee. I'm not enough of a coffee snob to really appreciate the benefit of the smooth pouring all over the grinds and stuff. But it looked cool watching it. Okay, one board flash. So unfortunately, I did not flash boards ahead of time. And I haven't even tested the image, which you can imagine is going to make for a really great tutorial. But hopefully there's enough on here that it really works. And we'll start this way since you were here early, and it'll be flashing boards throughout. Little micro SD if you'd like to copy the micro SD card. So you can I have 1 copy right now if you've got extra micro SD cards. I'd say double it once and then probably double it again when you start flashing with it. So the coffee machine was cool. Lots of other lighting display. The guys that did the Leadscape thing, they had a mega scroller. So they were playing Mario Brothers around in a circle. So it was like big enough that they would they had a wireless control, and as you controlled Mario, you had to actually run around the whole display to follow them around in circles. They're using the PRUs for lighting all the LEDs. And most of these motor controllers are all using PRUs, mostly using this machine kit distro. Because there you really don't even have to mess with the PRU firmware. They just have some PRU firmware that's set for driving stepper motors. And they just kind of go with it. All right, I'm Jason Kreigner. I'm a co-founder of BeagleBoard.org, and I'm a member of the local hackerspace, i3 Detroit. The guy that started up this meetup, David Shelton, took a job as an editor at Make magazine and moved away to California. He lives in Berkeley now, and just kind of saddled me with this. And you know, organization like this sort of thing has really not been a focus of mine. But I am at your service and happy to meet up with you at i3 Detroit if you ever have some Beagle project that you want some help debugging and need some things. I'm on the i3 Detroit IRC channel all the time, as well as on the #Beagle IRC channel all the time if you're familiar with IRC. And if I can't answer your questions, I probably know somebody who can. And that's probably more of my real value, is connecting me up with other people that really know stuff. So several of you are familiar. I think just a couple of you I don't know. Have we met before? I've been to PingleCon, yeah, a couple times. Oh, cool. You're Waldo.
You may have seen me.
Awesome. Yeah, but a lot of people have been really interested in these PRUs. A couple other unfamiliar faces. Have we met before? Okay, I am Jason. I've met most of the people in the room from going to Units before, and I don't think we've met either.
No, Peter, my
Peter.
colleague was Walter. He kept talking about BeagleBone, BeagleBone for like 3
Oh, there you go. I love it.
He's talking about his wheelchair, and I used to work for a company that made industrial balancing machines. So I did some training with my life program and things going around and everything. It was just interesting, especially with
Cool. Do you want to introduce yourself real quick? Hi, Jeffrey. All right. So I got started at this a few years ago. The BeagleBone. So I grew up in Texas. My wife's family is up here in Michigan, and we moved up here to be closer to our family. Yeah, I'm an employee of Texas Instruments, but I pretty much do BeagleBoard full time. It's cool for them because it promotes their processor. It's cool for me because I can actually just focus on engaging open source developers and hackers and do educational focused things. And so it's a nice thing, but they pretty much let me run with it. Not that they give me a lot of resources, but they do continue to pay my salary. So that's a pretty good thing. They also paid Gerald, who's the hardware designer. I'm the software / community guy. And more concept, but also dealing with all the Linux kernel craziness and stuff. We have volunteers that really do most of the heavy lifting. I'll also start flashing another board. Like Robert Nelson is the main kernel maintainer for BeagleBoard.org right now. He's actually an employee of DigiKey, if you know that company. So, some of these boards. It's the September 3rd image. But I've added a new kernel.
So what's posted is like a June or May build?
There's a May build on the latest images. You have to go digging around if you want to find the test images. There's a few things that aren't ready for prime time on this image. I kind of hacked the Bone 101 presentation a little bit to use Jekyll, and it needs some. So Jekyll, so that we can post it up to their GitHub pages. And so it's not really, so it's kind of messed up. We've been actually trying to focus on moving to the 3.14 kernel. I don't know. We should probably go ahead and switch over something fairly soon. But one of the other holdups is the new image has grown a little bit, and so fitting on the 2 gig card is a little bit more of a challenge. So the image that's under 2 gigabytes, now he's removed Chromium, which is the main web browser that's on there. So that's a pretty big subtraction. So that's another thing that's keeping me from switching it to be the main default image. But we've been shipping RevCs for a while, and a lot of people are getting RevCs to 4 gigabyte. We might just go ahead and make the switch so that we have a default 4 gig image, because there's enough stuff to kind of ship that's interesting, but trying to get it done right first.
BeagleBone's only got 3 gig on board, right?
The BeagleBone Black, Rev A and B have 2 gig. Rev C has 4 gig. And Rev C was the first one, I think, to ship with Debian as the default. Yeah, so that shipped the thing. And the Debian image is a whole lot easier to use than the Angstrom image, mostly because you can just kind of copy paste instructions from the web, and they just work because most instructions written for Ubuntu or for Debian. The other thing is the Cloud9 IDE, the version 3 that we put in the Debian image, it's much less buggy tremendously less buggy. It also has a built-in command shell that it just works. It's weird. This one's not flashing. This one's just running. Yeah. Try that one.
So which board has been flashed? This one?
Only that one. Only that one has been flashed. I'm not positive this is actually really set up properly as a flasher image.
Oh, the modeler and the innovators club or whatever. That's down in there. And of course, I remember that. Oh, you mean Maker Fair? Maker Fair, yeah. Yeah, we were at Maker Fair. Like I threw the Maker Fair Jason Fair. And you see those guys who were HHO welding torch. Yeah. Water. No, yeah, they use water jet cutting. No, water jet. Oh, okay. Great for water. Yeah, that's right. Right to it. And the size of the burner. But once that's fire brick or steel, stuff like that. More, I would be handling it. Yeah, I'm not going to do wrong micro. That was one.
Yeah. Not the one. It's a. You handed me a 2 gig.
Yeah.
Oh, you know what?
Yeah.
Yeah, that is a different one.
I had to do the wrong one.
Well, that would explain why it might not be doing the flashing.
Yeah, we copied to this one and then.
There we go. Now this is doing a flasher. There we go. That's what I wanted to see. Now it says it's erasing. The LEDs, when it's doing the flashing, does the little the siloning back and forth. That's how you know it's actually doing the flashing. Yeah. Very helpful. All right. Let's try to get into some PRU stuff so we actually have some time to talk about it, because it's a pretty complicated topic. Getting easier all the time, but still not quite for the every person. Everybody kind of familiar with what a BeagleBone Black is? No, not everybody. So it's one of these. It's a $50, a roughly $50 gigahertz open hardware computer. It's open hardware because you can get the schematics, you can get the layout files, you can get all the documentation for the chips without an NDA, and you can get the all the chips through distributors, in quantity 1. So if you actually wanted to make this, you could do so. They're also entirely based off of open source software. If you want to use the 3D graphics controller, that does require a closed source binary blob, which we don't even ship with right now. It's possible to go and get the binary blob to run the 3D graphics, but we're just not really focused on that. We're more focused on what you can do with the open tools. It ships with Debian on the onboard 4 GB flash and a USB cable, and that's all you need to get started doing development. You just plug in the USB cable, plug it into your computer, point your web browser to it, and you're ready to go. There are some drivers for Windows and Mac. The drivers are actually shipped on the board. It looks like a flash drive. You go open the README file, and it gives you the instructions for installing those drivers. You don't need to go download anything. A ton of people built projects and products around them. We don't really recommend. There's the buying the boards and putting them into products. Just realize you're responsible for that. don't hold us responsible for whether or not it works or not in your end product, and or whether or not you can get boards in a timely fashion, right? If you need to make sure you can go get them, go to a contract assembly house and have them made for you and own your supply chain. So, so any questions on what a BeagleBone block is? They're a lot of fun. You make a lot of cool stuff out of them. So these PRUs are these the Programmable Real-time Units. There's two PRUs as part of the Industrial Control Subsystem. So it's designed for being able to build up peripherals or interfaces to different types of devices. And in that Industrial Control Subsystem, there's two of these 32-bit RISC processors that each run at 200 megahertz. And they have single cycle access to different pins. You can get to all the other peripherals on the device, the standard GPIOs, the pulse width modulators, the quadrature encoders, all the other fun hardware, the SPI, all that. But there's some number of pins that have this really quick single cycle access. You can actually do like a set pin high, set pin low, and produce 100 megahertz square wave coming out just by bit banging in the software. In fact, somebody did for a Google Summer Code project. They made a 100 megahertz logic analyzer that's 14 channels, and they were actually able to capture 14 channels of data at 100 megahertz and stream that back up to the ARM, and actually do compression on that as they were streaming it back up. So they were able to capture over 1 gigabyte of samples at 200 megabytes per second. So really quick I/O, kind of optimized for packet switching type of operations and emulating different peripherals, doing soft peripherals. So if you wanted to bit bang things instead of dropping in an FPGA, it's kind of a bit of a FPGA replacement. So why and when do you choose to use the PRUs? One is the Linux operating system is just in your way, and you want to be able to bit bang at your leisure on these I/O signals without having either to have to go through different layers of the kernel, understanding the details of that code, or you don't want the latency, or you don't want the unpredictability of the timing. And really the timing is the main reason. It's real time because it cannot be interrupted from its given task, right? It will always, the next thing it does is execute the next instruction. Even in the case of getting external signals and interrupts. There's actually no interrupt vector. How many of you are familiar with interrupts? Mostly? Okay. So like most processors, when you get an interrupt, they jump to another location and begin executing code from that location. This processor doesn't. Instead, it just registers it in the interrupt controller, and you just, in your loop, you just go back and you pull the status. So there's a register that you can go and look at the status of the interrupts, and you can clear them, but it's not really like it doesn't go and change the flow and interrupt the process of what's going on. All right, so all of your code is in this event loop, where it just loops around and goes back and checks for new things to handle over and over and over again. Always done that way, and yeah, so that makes it providing very, very predictable timing. It also has really low latency from input to output. There's no pipeline. Even something like a Cortex M3 has like a 3-stage pipeline. The Cortex A8, that's the main processor that's running Linux, actually has a 13-stage pipeline. So, and pipelines help the processors go really fast. So if you're running a marathon, I mean, if you're doing a straight ahead sprint, it's perfect for that. But if you're trying to juke and be responsive to things, it's not always the greatest, because if you want to sample an input, it's going to take 13 cycles to go through that A8. If it's not doing anything else, go back and provide a response back to the output. I'm sure it's actually writing out at a little bit earlier pipeline stage, or there's probably closer to each other. There's several cycles away, whereas there's no cycles in between the operations on the PRUs, right? There's no pipeline. And one thing you can't do is, if you do need some sort of microcontroller in your system doing these sort of interfaces, one of the big reasons to use the PRUs, not just because they're fast and they handle these low latency things, but it's also built in. You can access all the internal peripherals of the device, including the external memory, right? So that logic analyzer I was telling you about, right? The reason it can work is because it's got access to that 512 megabytes of DDR that's shared with the A8. So you can easily stream data through shared memory buffers. That's also reasons why things like Leadscape, which Leadscape is this, it's a set of PRU firmware and some other software to go around it that uses the PRUs to dump data out to big LED arrays. So the PRUs themselves handle all the shifting out of all those LEDs, and it's a whole lot of fast data movement. But it works by just grabbing a memory buffer inside the A8 of what it actually wants to draw on the LEDs. So it makes it really, really easy to create software that I just write a Python script that dumps into a memory buffer what I want to draw on the sign, and the PRUs just grab it directly from that memory buffer and start putting it out. So that shared memory is a big deal. So the types of things people are doing with them, driving motors in a mobile robot, like if you wanted to do something that was like self-balancing, you can do self-balancing without the PRUs. There's the guys at University of California, San Diego, just did theirs as a Linux task, reading the IMU, or inertial measurement units at the gyros and accelerometers to tell you if it's moving one way or the other, and then setting the I/O pins in order to drive the motors. But having that low latency, predictable timing and stuff makes that a whole lot easier. So if you're doing that sort of thing, you see people switching over to using the PRUs. But for those sort of things, you'll see it really taking off in terms of CNC machines and 3D printers. So I want to very precise timing of when I send the pulses to the stepper motors relative to each other, so that I can get smooth motion of these motors and be able to move them as quickly, right, so that I can get get my 3D prints faster. Then the PRUs are the way to go. And there's this distro called Machine Kit, which is a Debian-based that includes the application Linux CNC, and they use that to drive all the G code for doing the CNC and 3D printing. And it also includes the PRU firmware in there, and for several different capes or add-on boards for the BeagleBone Black that have the stepper motor drivers.
And you use software on there, or you have to use someone else?
You can just, it actually has a GUI. You can actually do previews in 3D in the Linux CNC software. Build it? You mean build it?
Don't design.
I wouldn't author it in the BeagleBone. That seems unreasonably restrictive. I mean, you could, but it would be slow and painful, and you've got a fast machine somewhere else. Yeah. I mean, the idea that you want to do this, usually you want to dedicate it to some sort of specific function, like running your machine. You don't need to go and spend multiple thousands of dollars on a desktop, but you can't get all the IOs that you need to do to create that sort of system anyway. So you could try to make it a system to kind of be a replacement for your computer. But that's not generally a problem I try to solve with BeagleBone. It's not replacement for the computer. It's something that gives you an embedded system, or gets you something that kind of replaces the computer in a particular system. Agree, disagree, anything?
No, it's not an argument.
No.
That people put on there. Brought up a point that people might want to do it.
Yeah, and a preview makes a lot of sense. Yeah, there can be. I'm sure if you wanted to make some quick edits on there, I don't know what the Linux CNC capabilities are for editing. Where do I send flashed ones to? I'll just swap you out. Just don't confuse the flashed with the not flashed. Just make sure to remember if it's flashed, not to confuse it. All right. So protocols, different protocol generation. Like real-time communications protocols. All these are not programmed, right?
Yeah.
Okay. And that's something you do. Yeah. The Mindstorm's EV3 is based on a TI AM1808, which is an ARM9 processor, which is a bit older CPU, but they do include this PRU subsystem in that AM1808, and they used it because there weren't enough UARTs on the base chip, the AM1808. So they've actually using the PRUs to do software UART implementation on the Lego Mindstorms. Yeah, absolutely. Yeah, all the source for the EV3 is available. I think they have PDF schematics. I don't think they give you any layout files or anything like that, but then they do give you the Linux kernel source and the firmware source. So, in fact, somebody created this last week I saw on the BeagleBone mailing list. Somebody created an add-on board that gets you all the IOs for the EV3, and they moved all the firmware over as well, so that you could actually do like the whole Lego interface on the BeagleBone Black. Yeah. Is
it part of your library?
It's on the BeagleBoard mailing list, so you can find the links to it there. I don't know that he's given all of the right information for reproducing. I haven't found any schematics or layout for his add-on board. So it's some Fat Cat Labs. It's like an EV3. If you look for.
Oh, okay. So it interfaces.
Yeah, it interfaces to the Mindstorm.
Oh, that's cool. I mean, that's a huge market.
Tons and tons of projects of people using it. The pure use. I forgot to. I think the fourth interpreter is copied on. I need to try that out. I haven't even tried the fourth interpreter. Somebody did a GCC port for the PRUs. They started with the port for the Neos processor, like a synthesizable processors in the Altera FPGAs. They started with that, and they did and they made it work for the PRU instructions. There's a GCC for PRU. Yeah. So there's a TI. There's an official TI compiler, and it's a C++ compiler, and that's actually what I've got on the boards. What I flashed on these boards, and that's what we've got some different things built with. But there's also GCC, which hopefully we'll get the GCC shipping with the boards here kind of soon for the PRUs, and I think that gives us a lot more ability to kind of integrate more tools. But the tools are still very much in a early phases right now for the PRUs. Right? I mean, it's great for like deeply embedded systems guys, then that they kind of understand all the complexities of this stuff. Great. But for kind of the mere mortals, it's just starting to get there where it's where they're really programmable. And I'll show you what tools we've got with it. Mainly this PRU speak. That's kind of the example. It's not in the condition I want it to be in right now. but I'm trying to fix that. We worked with a student over the summer to create the initial port of this PRU speak, and then working with some more students now over in this count, this school year, to try to improve the quality of that code, make it a kind of a reference of all the different components that you need in order to work with the PRUs. So it's just out of the box, you can start sending it commands, but then you can start peeling back the layers of a PRU speak if you want to replace the firmware load, if you want to replace the device tree entries for the configuring the I/O pins, you want to replace some of the interfaces at the kernel module, and the communications between the Linux kernel and the PRU. All of those are given as examples, and you could kind of peel back the layers of the onion.
You're not talking about are you talking about those going direct to the PRU?
Yeah. They're GCC for the PRU. It doesn't save you from the need of, and I'll repeat this. I'm going to go through this in some detail, but there's kind of 4 things you kind of need in order to use the PRU. All right, you need the firmware, which the GCC will help you make the firmware. You need the kernel driver to do the firmware loading. So you need to load the firmware onto the PRUs. So you need to create the firmware. You need the kernel driver to load the firmware and then also to talk to it. You need the device tree entries, which configure the kernel, and that also helps you configure the I/O pins. All right, so there's that. That's just kind of a configuration file, and then you need kind of the communication mechanism back and forth between the two. So whatever kind of protocols you create for communicating back and forth, you need to kind of have those implemented in the firmware side and in the kernel and user space. Right. So those are kind of the different levels of things. And for PRU speak, we'll have an example that gets you all the way down to communicating and sending commands and doing stuff on the PRUs. And then you can just, over time, just make changes to each one, right? So this eye chart is the basic architecture, limited to 8K in program memory, and each of them has 8K, and you're limited to that. That's all the code it can run. If you want to be able to run bigger programs, you'll need to copy more program stuff in. So you could potentially page more code in, but generally the stuff you're trying to do is tight real time anyway. And you don't need to mess with that a whole bunch. They also have a separate 8K data RAM for themselves that they can work with, and 12K shared data RAM between the two. So they can use that to communicate back and forth between them, or just kind of allocate chunks of it for whichever one you want them to use. But they can still access external memory, so they can get to the 512 megabytes of DR. But that's generally for like bulk data. Screen memory, they could probe any of the DDR memory, but you're going to need to kind of do that physical mapping in order to find out. But potentially, yeah, you could talk to the frame buffer. You could. There's not a graphic card. You have a. There's not a. No, it's all in one. What's called a system on chip. And in the system on chip, there's the way that the LCDs or the HDMI and all that stuff are talked to is through this thing called an LCD controller, LCDC. And all it does is it grabs this buffer out of the memory and it shifts it out over the pins in a certain pattern. And that's really, for this chip, as far as like the display controller, that's all it does. Some chips have more sophisticated display controllers. This one's pretty darn basic. It's entirely programmable. You can make it as big as you want. The clock rate on the LCDC controller is enough where you can do 1920 by 1080 at 24 frames per second. And that's what its data rate of moving data out from the DDR3 and into the pins is kind of limited at. Is that what it is? Your math, your arithmetic is way better than mine. 1920. So two by one.
2 by 1. 24, 25.
Okay. But times multiple bytes, right? So you can do that with 3 bytes, right? So 24. So times 3 is 150 megabytes per second. If that's right. Yeah. So that guy will just dump stuff out to the LCD pins. You could potentially access that same memory because it's just DDR3 memory from the PRUs. So if you wanted to, you could have the PRUs do color space conversion for you, for instance, in your frame buffers, and that would probably help speed up some of your like video playback. Similarly, the 3D graphics engine, right, has just direct access to the DDR. All right, so like when you're rendering 3D objects, all it's doing is rendering them into the memory buffer. If you look at the original BeagleBoard, it has a more sophisticated display controller that actually has multiple planes where it's doing overlays and doing color space conversion in the display controller, but not this guy. This guy is meant for pretty simple display systems, right? It's targeted mostly at like point of sale, point of service applications or navigation applications or industrial controllers, not so much like video games. Yeah, it's not a video game device. Although it runs MAME fantastically, right? If you're just doing, but they're pretty low requirements for speed. Exactly. There's also a bunch of other peripherals in here for doing things like parallel and serial capture. So it's like there's like you can write out to things, and there's shift registers that you can write out to. So you don't have to manually shift out each bit if you're trying to do a serial protocol implementation. You can use the shift registers and clocks tied to shift the data out. So if what you're trying to implement is a UART or like an SPI like bus, you don't have to do raw bit banging. Although kind of the first pass approximation for most people is that even if they're doing serial protocols, is to write a bit bang, which is how I wrote the LCD controller. Right, I just did pure bit bang, set pin high, set pin low stuff. The low latency pins are these 25. The ones with PRUs. It's the light color. It's not so visible up here on the screen. But these are, so the different PRUs, I think R30 is input and R31 is output. So like there's the register bank in the CPU. It has 32 bit registers, 0 to R0 to R31. And those last two registers, it's kind of sort of classic load store architecture, RISC architecture, about CPUs. But those registers themselves are directly tied to I/O pins. So each of the pins on the BeagleBone CAPE expansion headers have all the digital I/O pins have 8 different modes that can be multiplexed. Like some of them will be UARTs or arbitrary encoders or I2Cs or the LCD pins and all sorts of different ones.
Which side did you start out with?
The left, if the Ethernet jack is on the top, P9 is on the left and P8 is on the right. Yeah, and it's written very small on the silk screen. And I try to refer to them always because that's the only thing that you'll find in the silk screen on the board is P8 and P9. So that's why I chose it. Who's next for flashed board? Yeah. Just remember which ones are flashed, please. And of course, I haven't tested the image, which will make for a really interesting day. Okay. So you see PRU 0 and PRU 1. So depending on which PRU it is, And one thing I remember I did not do on the image was turn off the HDMI, so I'll probably have to go and edit the files. And one of the first things we'll do, I'll show you how to edit the boot script to actually disable the HDMI. Because the HDMI takes a bunch of these pins, because that's where the LCD signals come across. It's kind of a virtual cape, because the original BeagleBone didn't have a built-in HDMI. You could add it on as an add-on board. And all we did was just take the logic from the add-on board and put it down on the main board. So you can disable it, and you get all those pins back. If you leave it enabled, those pins are busy driving the LCD. So these pins are ones you can just directly peek and poke at the registers. And if you want to boot up some of these pre-flashed boards, that'd be good. UART 0 here. That's yeah, this UART, there's actually a UART built into the ICSS.
So is that one of the pins?
Yeah, it can be mapped out to some of the pins. So it's part of the industrial controller subsystem. I'd have to look at the different MUX modes to see where that comes out. But yeah, essentially there's a UART as part of there, which you can actually use the UART to talk to the PRUs. There's this. There's like a whole bunch of code coming from TI as examples. Let me actually look. It might even be live now. Sounds pretty practical. You know, there's not a particularly preferred place. Special computing is pretty good about keeping stock, which is why you'll find them first in the pull-down list. I happen to really like Adafruit. You know, I believe in supporting DigiKey because DigiKey pays Robert Nelson, which is awesome. Element 14 makes a clone. And if you buy the clone, it's the only way that the BeagleBoard.org Foundation is, other than Google Summer of Code, buying boards from Element 14 is the only way the foundation is getting any money. So they pay a small royalty for using the logo to make their clone. And so that supports the foundation, so that's good. Their boards are made in China, where the other boards are made in Texas. So use your own value judgments there. They have some really nice cases, especially their. Yeah.
And they have some nice new boards on some capes on sale right now. It's got an XP cape.
And I like SparkFun, but both Logic Supply and Adafruit are doing more to kind of build tutorials up. So yeah, thanks for the Logic Supply.
Is there any place in town that actually sells them? Micro Center besides
Micro Center, Radio Shack.
Radio Shack?
Yeah, Micro Center and Radio Shack.
Radio Shack,
they only have the kits.
Okay.
They only have the make kits. So, and MakerShed is a good one to support too, and Make Magazine in general, because they've been doing all these weekend projects. So they just released several weekend projects based on the BeagleBone Black. Gosh, there's too many people to plug.
Yeah.
There's tons of people selling it.
Well, once we boot them up, is replace them.
I go to Cloud9 IDE and do a uname-r to make sure I got the kernel installed.
How do you get the Cloud9?
Just you can click here, and then click there. Yeah. Actually, just change it to port 3000. That's that bug I was telling you about with the Jekyll thing. Just :2:3000, or just period 2:3000, and then port 3000. Okay. So you're looking for some code to, I recommend downloading this, which is the PRU software package. That should include some code that talks to you how to use the different peripherals. I haven't looked at this actually. Gosh, it's been built since June. I should really play around with this. That was the there's a TI set of examples, the PRU software package. I know it includes things like building a software UART. I'm not sure if it includes something using the UART as part of the peripheral. I would imagine they do, but I haven't seen that. Also, a link here on the wiki. There's this list of PRU projects, which all these include examples of programming the PRU, right?
What's that website?
Processors.wiki.ti.com. Look and just do PRU-ICSS. It's the PRU Industrial Control Subsystem. And I will definitely take a look at that library. There's also the starter. If we're using the peripherals outside of the ICSS, like the general peripherals, there's this library called Starterware, which has code for doing the USB, the I2Cs, the SPIs, the NMC, like all those different peripherals without an operating system. And you know, we've compiled that for the PRUs and used it a couple of the different libraries without really any headaches. Other than you need to make sure that you disable the Linux kernel access to the peripheral, like take them out of the device tree or somehow otherwise prevent the Linux kernel from coming in and trying to use those, because that would be bad juju. Like I said, you can get to the other peripherals. This L3 bus is the terminology for the internal bus layer, where you can get to all those different peripherals. If it's a peripheral on the L3, you can get to it. Be careful. So the tools are really starting to mature this year. You know, I'd say we're, you know, by early next year, this can be like really easy to program. You know, like just as easy as other microcontrollers. I know there's a port of the Arduino IDE to do Arduino style programming, the library for the PRUs.
Is it like matured a little bit?
It's still ugly to me. I know. It's still pretty ugly though. Yeah. It still looks like a student project. It's still pretty incomplete. So yeah, still trying to bring it over the finish line. This is the one I'm trying to push on, and I'm not too super happy with the thing yet, the PRU speed, but as a general, I like the idea of just being able to type in commands immediately just to a file, and I'll show you how that works. There's a TIC compiler, GCC4, this PRU speak, and it's Starterware library, and I didn't know there's the Arduino stuff from the folks at John Brown, and then there's the TI examples now as well. So again, there's kind of the four components for talking to it. You know, you need some sort of the Linux kernel driver. There's two main drivers out there. One's been in the mainline for a while, which is this UIO PRU-ICSS. That's all that does is open up the registers to the PRU your application running in the Linux kernel, right? So it just says, okay, I'm just going to memory map all the registers, and then you need still a separate library that understands how to write to those registers in order to trigger loading of different firmware. We've been shipping for a while with a library that has a set of functions that you can use to load your firmware and just to interact with it that way. It's kind of not the preferred way to interact with it, because it doesn't use the standard Linux kernel firmware loader, and you know, so it's not really properly abstracted from the Linux kernel as a processor. So new development is going on for this remote proc interface, and the difference between that is the Linux kernel actually knows how to load the firmware using remote proc. So instead of it being done in Userspace, the kernel itself loads the firmware. Then you need some way to actually communicate with it, either some sort of Userspace application or a kernel driver for the application, device tree entries, configure the pins in the driver, and then you need the actual firmware. Right. So those are the main components. And the example we'll work with is this thing called PRU-ICSS, right? So it's a completed firmware, ready to run. It was done as part of the Google Summer of Code. And it's still not quite ready for prime time, but I've pushed it into the 3.8 kernel that we've got for download for the boards. Huh? It's actually not shipped as an image yet. It's just a Debian package of the kernel. So what you do is, and that's what I'm flashing on here, is you actually download the Debian package, install the Debian package on like one of the like the 9.3 image or one of those, and then you'll have it. So another flash board. These are all unflashed, right? So actually, I'll probably want to plug in a flash board here fairly soon. This is just flashing now. Is that one flashed? Okay, not flashed. So next major release that we'll have, we'll include that. It's an implementation of this thing called BotSpeak. So BotSpeak is an interpreter that's implemented on Arduino, on Raspberry Pi, on the BeagleBone Black and the JavaScript interfaces, and it all just is a way to just kind of normalize the interface to the to any CPU, right? So it's got the basic operations or things like set digital I/O and high, set digital I/O and low. But it's all just kind of like in this assembly-like language. But the nice thing about it is you can because it's a normalized language that targets all these different other platforms. You can have integrations to other higher level things like LabVIEW, right? So the guys at Tufts have a way if you program with LabVIEW, you run these VIs and it'll generate the BotSpeak code, and you can connect those up and just send the code down to the boards. Unlike Firmata, anybody know what Firmata is? So Firmata is a standard firmware load that's used on a lot of Arduinos, and it's pretty common for like things. If you want to interface with higher level languages like say JavaScript, like a lot of the people building JavaScript-based robots will take an Arduino or even a BeagleBone and implement Firmata so that it abstracts the IOs. But it's kind of a configuration-based interface, right? So you can say, blink this pin, at this rate, or set this pin high, set this pin low, as individual commands, but you're not moving logic down to the board itself. All right, so it's kind of got its set operations. It's more just a configuration that you can change, not a not something you can actually make decisions. So if you're trying to do like a PID controller, which is what you need to do for like a balancing pod, or read from some sort of accelerometer or gyroscope, Firmata wouldn't really work like that very well. So BotSpeak does. It looks like assembly language. I don't know if how many program in assembly? A few people, okay, or a little bit. So we're going to program in something that looks like assembly today. Then and the way that you talk to BotSpeak is you can talk it over serial or network, or just a web-like interface, and it includes Arduino-like operations. It's kind of built on top of the Arduino API. So we play. I need one of I'm going to borrow back one of the flashed boards so that I can show. So that way I can have the same warts as opposed to using my board that I know works, and I know I can do the demo on. I'd rather run into the same headaches that I'm about to send you into. So you give it a minute here to boot. When you plug in a BeagleBone Black, that uses the Linux kernel to implement a few what are called gadget interfaces, and those are those are client devices. So it looks like a flash drive. It looks like a serial device, so you can do like communications to the command prompt. It also looks like a network device, and it automatically starts up this this web server on port 3000, which is the IDE. Oops, open. It is Cloud9 on 3000. There's a node server on port 80 that's not.
Yeah.
Right.
You're just using it because it's got the terminal.
I'm mostly using it because it's got the terminal. I will do. Oh shoot.
Cloud9 doesn't support.
Well, I mean, it's just Python. Like so.
Oh, okay.
So like the way to talk to PRU-speak is you can do it a few different ways. You can start this TCP server, which will have it listen to a socket. In the future, it will just be a file that you can read and write to, provided directly by the kernel. But right now, the implementation is there's a Python layer. It's doing the tokenization, and then sending bytecode on down to the PRUs for execution. So there's just this PRU-speak library, which hopefully is installed. And
is it on Python, like, is it in pip or like?
it's not in pip right now. I just made the setup script today to actually install it into dist releases.
Okay.
But eventually it will be in pip when we ship it with it. Actually, nobody. Let me make sure I've got the right kernel. That's good.
So if we use this build.
If we use this build, you've got it.
You got it.
So one is this kernel right here that has it. I've got that off of builds.beagleboard.org. You look at the grid of the different builds. So here's like the latest 3.8 build, but you see I did this Bone 67 PRU-speak build.
And that's got the Python set or this code.
That's got the device tree overlay and the kernel driver. So that's those two components.
All this code that we have here.
That is from the PRU-ICSS repo. If you look under source, Userspace lib, that's all coming from here. Actually, I shouldn't say that. It's coming from my fork of it. So I got that kernel from there. I got the Python stuff from there. The firmware is also from here. So I built the firmware. The PRU firmware is coming from here.
It's all from here.
So if you look at there's two firmware files, PRU0 and PRU1. Those are built from these C libraries, those C programs here. So what I can do, I'm going to run this this one that's the TCP server. But before I can actually run it, I have to load the kernel module. So I do mod probe. Oh. That's how I load the PRU-ICSS. Yeah, and that's the issue I was talking about before about the I/O pins being used by the HDMI. I know you can't see the bottom. Maybe if I take this off of full screen and I just move this up.
Yeah.
So there's two things I need to do. One is the mod probe of PRU-ICSS. That loads the kernel module, the kernel driver. But I still need to do the configuration, right, of all the I/O pins. So I need to load the device tree overlay, and that also sets up all the configuration parameters and sets up the firmware that's actually going to be loaded. It actually specifies the names of the files for the firmware that's going to be loaded. And that's this config pin overlay. If you've seen BeagleBone Cape stuff before, you know, all that config pin is doing is writing into this slots file. But if I do config pin overlay, and this is the name of my device tree, is bb-PRU-ICSS. But it's complaining. So what I have to do is make sure it's not mounted.
Error.
I'm going to unmount it from my Mac.
I'm having trouble with the config pin overlay also.
Yeah, it's because of the HDMI pins. So I configured some of those pins to be used.
Okay. And how do I
So I mount the partition of the FAT. I could have done it from my Mac, but I unmounted it from my Mac and then mounted it to my from my Linux machine.
Yeah.
Actually, you know what? We now have a copy of it running. We have a second one running on the exe file system, so it's much safer just to edit that one. So forget the all mount stuff. We now have two unv.txt, one that's on the exe file system, and that's the one that's safe to edit from the BeagleBone Black itself. But you'll see this line that says disable HDMI. It's /boot/uenv.txt. I used VI. Let's use Nano. So Nano.
/boot/what?
It's lowercase u, capital E, lowercase nv.txt. So I should meant to do this before I copied all the boards.
That's it.
Sure.
I mean,
yeah, it's nice to be able to work this on the fly.
I wouldn't know
What's going wrong, right?
My cable on. Why isn't my display working? And so,
So we've got another board that's flashed. Anybody else ready to? That's ready to program.
I'm sure a lot. I think I get it.
You just need to expand your view for one. Where's your button? Okay, just grab that bar. This bar, this one? The bar. This bar? Yeah. You can grab it.
Grab it. This button.
Left click it. Here, I'm done. Isn't that right click?
I get some of it,
Oh,
and get these back down below there. I have this stuff at the bottom.
Right click.
Did you do the module?
I don't think she has a console. Right?
No,
UNV.txt.
How do you use the console?
Oh.
You just bring it up from Cloud9.
It's just down at the bottom of Cloud9.
We'll say
yeah, I don't know. This is as far as I
text
got.
that's got the file for all the pins, right? Or
No, it's just the boot configuration file.
it's like virtual case or real case.
So we go down here to the HDMI.
Which configuration yeah. Oh, disable HDMI comments.
Just press enter, it's going to reboot.
You want me to put that on now?
Yep.
Okay, so I got the two hash marks. Do I delete them or something?
Just delete the one hash mark below it, and that's the eMMC. You want the HDMI, not the eMMC.
Okay.
You don't want to disable the eMMC since you're trying to boot from it.
All right. Okay, so just the HDMI line.
It may not boot again.
The HDMI line.
Yeah, no, don't delete the line. Just delete that one comment. So there's
so it's now
beforehand there was a little hash mark here, and you want to remove that because the hash mark is a comment, so it actually ignores the line. If you remove the hash mark in front of it, it then knows that it actually wants to use this.
How do you close?
And these are the virtual case, the HDMI and the HDMI no audio. So it's going to disable both of those.
And how do you save and exit?
You do Control X and then do Y. Control X. I didn't have to do Y because I'd already saved it.
Y.
And then hit Enter. Control, yeah.
Right.
And then we do shutdown -R now. And we'll see. I can't.
Down -R for restart.
My screen is way too wide.
Shut down.
Yeah, and you see my Cloud9 will eventually say offline.
It's telling me I've got a usage problem. Shut down.
Yeah, but now.
You have dash shutdown -R space now. You have to tell it now. Sorry, just now getting yours up to flashing.
Yeah. So I've got this one is done. I think everyone's done. Right? Yeah. There you go. And now
Yeah,
after
it's still-
this, we do
I don't know
big
if that's
overlay or just not. We don't need to do that anymore.
What's the question?
So after we fix that file,
Yep.
then after we boot it,
We still need to do mod probe.
we still need to do micro.
Yeah, because we haven't. There are ways to make it not have to do this manually, but I left this step manual so that you knew what was going on here. There are files that we can edit to make it do this, both of these automatically. Like that enable cape thing, we could do the BB-PRU speak in order to get it to automatically load that device tree overlay, because that's what the disable cape manager and enable cape manager, those are all just telling it what device tree overlays to load for what configurations. There's also a file to tell Linux what kernel modules to load on boot. For the moment, I don't actually remember where it is, but it'd be pretty easy to find.
This is just a Linux file, not a firmware or anything like that. We're modifying.
Where you're talking about firmware for the PRUs, or what are you talking about when you mean firmware?
Talk about firmware. I don't know what you use to here. Typically, there's a firmware built into the hardware. So you change that. You're changing
the only thing you can change on the BeagleBone Black is the contents of the eMMC. Unless you actually short a wire, you can't change the contents of the EEPROM that's built in. So if you short one wire, you can change the EEPROM, but you can't actually change the ROM. You can't change anything that's going to brick your board. The worst thing you have to do is if you say it's brick, is that you have to go to boot to an external eMMC in order to reflash your onboard eMMC. So you can't actually overwrite the firmware of the device itself. It's all read-only memory. Okay. I found one of them that wasn't. Unfortunately, I recycled it.
There's one here.
All right. I'm ready to see something work.
All right.
So the I've already done. I did the mod probe. I did the mod probe PRU speak, and then did the config pin overlay BB. Notice this time it didn't give me an error. Yay! My HDMI isn't in the way. And if I wanted to find out what that error was, I actually have to look at dmessage. That's the kernel log. But if you type in, DMESG, you get that kernel log. You can see here it successfully configured the PRUs, and it's all happy, hunky-dory yet. So you can look at all the different success messages if you want to look at them. But this BS, it's how appropriate. The BotSpeak TCP server, if I just run that, it's a Python script. Oh, shoot. Ply isn't installed. Oh, no.
CLI.
Oh, no. It is Python. It's a lexical analyzer. It's like Yak or Bison. Yeah, so it's a module that I depend on. And I thought I copied it.
Converting Python to
Yeah. User local.
Python based actual.
Oh yeah, there's no ply here. I got PRU speak, but no ply. All right, I'm gonna try to do something crazy here. I don't know how everybody else is gonna do this, but
Is that not in pip?
it is in pip, but I need to be on a network in order to.
You're not online?
I am. My BeagleBone isn't.
Oh, of course. Yeah.
I need an Ethernet cable. If I had an Ethernet cable, it makes it really easy.
I got an Ethernet cable.
You know, why don't I? Okay, let's really put this in our pants. Let me.
Download it once.
Where?
All right.
Oh, USB.
Now we're doing this.
Well, do we
Try
have
to do
a
that.
wired Ethernet here?
Right here, I think.
Do we have access to it? We'll get it.
Oh, well then
Oh, you got one.
let's cheat.
That was my thought.
If it gives me an IP address.
How are we gonna get that to everybody else?
We'll pass it around the cable one at a time. Or we can put it on a USB drive. I don't know if anybody, does anybody know how to copy a Python library? Right? I've never done that. I've always just used pip to pull it down from the internet. But does an egg have all the content? The egg has all the content, or is it just the? Yeah. Looks like I have an IP address, so pip install apply.
Yeah, there's like a cache, I think.
How much room is on this image anyway? Okay, it's got a decent amount.
And 5 is lowercase.
You got 140 meg free. That's lowercase. All right, let me try running the TCP server again. Oh. Now what that allows me to do, there's a great utility called netcat. The way this will work in the future, when actually I'm done with this, is there will just be a file that you can read and write to, as opposed to using a TCP/IP socket. You still can use a TCP/IP socket if you want, but so right now, if I want to say run something on the PRU, I can do a set I of a.
Instead of TCP/IP socket, you use what?
A file. I'll just read and write a file. So you could just do like screen if you wanted to in that file, or you know, because just that file would just be something that you do I/O into. No, you have to go through network for the TCP. It would actually be faster to just do a file.
Network stack.
Yeah, the file I/O stack is there's less layers going through a file I/O stack. There's no
That's only going to come into play if you were trying to get close to real time, right?
Well, all the real-time stuff offload anyway, right? This is just for talking to it. So I now stored a variable onto my PRU, right? This is not PRU assembly, this is bot speak stuff, which looks just like assembly, but I set the variable I to be AA. So I can get the variable I, and it still has the value AA. I can set the variable J to BB, and I can get the variable I, and that variable I is still 170. Yay, or AA.
Awesome.
But let's do something fun, and
So you don't need to keep all your work.
I can pass the Ethernet on, and I needed to do DH client for some reason. It probably would have eventually got back to running the DHCP client, but I just forced it by running DH client manually. So P9
It just needs to be fit, right?
is the one on the left. So I happen to know. I happen to know pin 42 is P942 and P942 is GPIO 4 on the PRU 0, and P946 is ground. And this LED has a resistor built into it. So if you wire this up on your breadboards, I advise you to put a resistor in serial. But P942 and ground, and I can do set DIO 4 to 0, and my LED goes off. And I can do set DIO 4 to 1, and my LED goes on. It's magic. But the nice thing, so the whole purpose though of bot speak isn't that I just want to sit here and type individual commands into it, But I do have this ability where I can like have a high-level language like Python, yeah, and I've assembled REPL, which is a command line interface for those that don't know. But that's kind of cool. But what you can do is you can start a script by typing in the script keyword. So if I start a script, I could do something like set the IO for, so let's start with high, and I'm gonna wait 100, which is 100 milliseconds. Set the IO for to 0, wait another 100 milliseconds, then go to 0. Oh man. So you can create labels. Labels in bot speak are variables. So if I were to create a label, it would remember what that number is so that I can go to it. It's kind of ugly, honestly, so it's not really super great for coming up with functions and stuff. And it'll probably make some improvements to the language in order to really make it work nicely. But go to 0 will take me back to the beginning. I then do in script and the magical run blinky LEDs. Nobody's nearly as excited as I was for that.
Well, everybody's trying to
I'd
catch
be really
up.
excited if it was a 2812.
My life.
If your light was blinking.
I got yours.
Anybody else need a flash board? Are we done flashing boards?
Good flashing board. You guys have one? Yeah.
All right. So can we remove all non-flash boards from the table so that so all the boards on the table are flashed?
This one is in process.
Yeah, because I just need to mark those differently when I put them back in the box. Just so that I don't waste extra time.
That's a local ID. Well, yeah, it's going to be local, but that's a good deal.
So while this is running, I can actually do things like, I don't know, actually, I've never tried this actually, but you can do get DIO4. The chances.
Yeah. You want to catch it if you want, right?
It seems like randomly I should be able to get back a 1 at some point. So maybe it's not implemented, actually, the get is not implemented properly. And if I want, I could start a new script. But typing in all these scripts like this is kind of a pain. This circle that's running right here, this is my Python script that's listening to the TCP/IP port. Right now, the implementation is there's a Python script that's doing the tokenizing and assembling it down to bytecode. It's shoving the bytecode down to the PRUs that's running the interpreter. So the PRUs aren't actually looking at the text strings, they're just looking at numbers.
So how do you do that? Do you go through a shared data?
Yeah, there's a shared memory buffer, right? And there's the interesting part. So now we're gonna kind of get a little bit familiar with this, and we're gonna start peeling back, depending on how much time we have, the layers in the onion to see how this is implemented. And I don't know that everybody has to get to the point of blinky LED. It may not be that interesting to everybody. But for some people, just being able to do that sort of stuff is kind of cool. Right. So other scripts here. With the Python stuff, I'm going to just go ahead and stop this TCP server. Notice the thing still keeps running because it has absolutely nothing to do with the Python code that's running. It's running independently. All right, so I don't have to keep talking to it or anything. It's not that CPU is just running entirely independently. But here's some other scripts. This one is actually testing something and wasn't implemented in the interpreter, which caused me some headaches when I was trying to create my my interface to the LCD modules. I'm just gonna skip that test. But here, so I could use the Python interface to the PRU speak to run these several scripts one after another. So this first script is just going to load a essentially a blinky LED. But see here now, the delay is actually programmable. It's a variable. Did you want to install pip?
No.
Or install
Or PLY, pip install PLY. I've got another flash here that, so at the in the script it says go to loop, whichever loop is running. So I started out with the loop being set as flash. So you can see you can have variables and store the branch addresses to. And then if I change that to flash 2, you can see it's going to do a blink twice and then have a twice as long delay. And so I have that script, that's my script, and then I can immediately execute these couple of other commands. And this is how, with PRU speak, this is how I can create the dynamic communication between the two, is that I can always go back and update variables, right? And it's doing that with shared memory. It's loading the program to shared memory, and then I can use individual instructions, and, or use shared memory in order to communicate. So here I'm just going to update the variable loop. To start it out, I'm going to run the loop flash. Then if I want to do the double flash, I'll set the loop to flash 2. Yeah.
Okay. So
so now when it runs, oh, what is it the right?
okay. So once I have the server
Got some
running,
fail here. That was interesting. It didn't work the first time. I don't know why.
okay. So I've got the server running.
No.
Then I opened up another window and I started netcat, which is NC. So netcat is just a Linux utility that you can use to open up a T-port. And so are you familiar with the Linux utility cat? C-A-T?
Catalog?
Well, yeah, it just provides like a file I/O from a program. Like if you type cat in a file, it puts that out to standard out. And if you write into cat, it takes standard in, right? So it's just a standard in or standard out or standard file I/O mechanisms for Linux. Netcat does the same thing but with TCP/IP ports. So it connects a TCP/IP port instead of to a file, or standard in and standard out instead of being to a file, it connects them up to a TCP/IP port. So you can do netcat space localhost because it's running on your machine, and then space and then 6060. That just happens to be the port number that we're listening to.
Okay.
So now I've got blinky LED. Right now I can see I can create a program, start doing some I/O basic operations. And the the overhead of this is reasonably low. Like if I wanted to, I could set the delay here to be. Let's set the delay here to be 1. So first it starts at the half second and it updates there. And so that's faster than you can see, right? You can tell it's on half the time, but yeah, because it's dimmer because it's on half the time. So it's, you can hook up a scope to it and see how fast it is. It's just run this BSTCP server right here. It's underneath examples PRU speak.
Yeah. So what do you mean by starting another window to run the netcat?
Just in the terminal shell. So like you see bash at the bottom. Oh, hit the plus sign. Hit the plus sign and say new terminal.
Oh.
And that gives you a new terminal window.
Oh.
So let's look at how some of this stuff is actually implemented. And for that, I'm actually just going to go up to it on GitHub, because I think it's a nicer way to browse all this stuff. So this is the I'll show two GitHubs, right? Because this is the PRU speak that has all the Python and the firmware for it. It's also got the kernel code, but it's not the kernel code we've loaded. For the kernel code we've loaded, we actually go and look on the BeagleBoard Linux GitHub, because that's stuff that's actually been integrated in with the BeagleBone Linux kernel. And if you're looking there, if you look at firmware and capes, firmware capes has all of the different sources for the device tree overlays for the BeagleBone capes, right? And this is all in the 3.8 kernel. We don't currently have overlays for the 3.14 kernel. So they're all just static. But for this one, and this is what the device tree overlay looks like. There's a lot of information out on the web about the syntax for these. But what it's doing importantly is it's reserving the I/O pins that it wants access to. It's leaving out pins that have conflicts, like the ones that are used by the eMMC. But it is using the HDMI pins, right? You'll see a bunch of these are actually used by the HDMI. So when you try to load it, the device tree overlay is a modern Linux kernel thing used primarily for ARM devices. What happened was Linus was very irritated by the sheer number of ARM platforms and how divergent they were, and how complex they were, and all the complicated code that was going into decision making about the different peripherals that each of the different devices would have. And so he said, I'm not going to take any more code for all this stuff. It all has to be generic, and you need to use a device tree overlay to make all the different weird configurations for the different platforms. So it's just a mechanism to move what was once in code to be data driven.
Right.
Yeah, and because he doesn't want to mess with all this multitude of platforms, so just make it configurable, and use a common interface for all the configuration parameters. So all this is it signs matching things like it's compatible with BeagleBone or BeagleBone Black. Those are ones it can load on. It's setting up some elements for use. But here so the normal mechanism for device tree is at boot time. There's this one description file that describes all the hardware that you're going to use. Mm-hmm. Device tree overlay allows you to change that after boot time. And for things that you're doing where you don't know exactly like what you're going to wire up, right? Here we're wiring up stuff to the PRUs. You may want to use those pins for, say, the HDMI or other things like that. We don't want to bind those in one place to the hardware. So one solution for that is these overlays. And here there's a pinmux that gets configured, the AM3X pinmux. So we're taking that in the device tree, and we're overlaying these values. So we're changing the set of values that it has already assigned for that peripheral, and we're changing it to be these values. So if there's a conflict in the change you're trying to make, your device tree overlay may not load, right? It may fail when you try to load it, which is why you see we're trying to allocate those different pins that it was failing because HDMI was already using it. But here it's setting up, and all these numbers are a little bit magic. These happen to be the offset, the pinmux peripheral, the offset to the register that controls this pin. So,
so normally you would do that at EOP, like you did an embedded system. You would write that out as part of the EOP to configure the I/O registers and all that.
Exactly. Well, because now we move it to an overlay because we want people to be able to develop a bunch of different types of systems, not just one. Yeah, the kernel driver. Yeah, the kernel driver is doing that back behind the scenes. So each one of these like it's selecting the different modes. Like you see the last 3 bits in this register is the mux value. So you can see it's mode 6. Mode 6 matches the 6 here. Mode 5, So that's the pin mux mode that selects the PRU to be the output on those pins. So that's how the pins become allocated to the PRU and actually manage to get out to the actual physical pins. So if this isn't done, right, you can set those pins high and low all you want at the peripheral,
Right.
in the PRU, you never see them on the output pins.
What's this file called?
It's BB. Remember when we typed config-pin space overlay space BB-PRU speak? This file is called BB-PRU speak. And then there's a version number 00A0 and the .dts or device tree source.
Device tree.
It's a device tree source file.
I got an error when trying to run the STCP. I just ran it right from the interface, like I clicked on the tab.
Yeah, that's how I was running it. Well, the module's not loaded. You have to do mod probe and the
Which file?
victim.
I got the
Oh,
server
okay,
running.
let's-
I got the server running, but I don't have the example program. Which example program do I run? So I've got PRU speak server running.
Yeah,
Then I've got the netcat going. The netcat going. So I got connection.
You're ready. So over here, you can start typing commands. In netcat, you can start typing commands. In this tab, in that tab, you can start typing commands like set.
Capital, does it matter?
It does matter. It's the commands in bot speak are all caps.
Set.
Variables are mixed, but the commands are all
Okay, so I
uppercase.
set the light.
No, just run this.
DIO.
Switch to this tab. That's what we got.
Capital
Of
or
course, you don't have a, I don't know if you have a light actually wired up.
Well, it's
It's on a different pin.
Right.
These are wired up for a totally different lab.
Oh, that's directly
Now
in.
you're.
And this one has a resistor built into it.
Oh, okay, different light. So I
just like.
can't
I can
use
give
that.
you one of these LEDs that has a resistor built into it.
And then I connect specific pins.
There's a gray case here somewhere. Here it is.
So yeah, you're good to go there.
These little LEDs.
Unplug your.
I bought special LEDs at one point for different labs. The last people, this was used. These boards get shared between different workshops. They were used in ASEE, which is the American Society of Engineering Educators. So there's one that has the resistor built into it. And they ran a certain workshop, probably the same workshop we ran from last year. And they were the ones that left these boards set up. Yep. All right, so device tree, that one's the easy part. Now we get to more fun stuff.
Okay,
So the inside of, so the kernel driver is here under drivers remote proc. You'll see the BeagleLogic example. I actually pulled a lot from the BeagleLogic example in order to do the PRU speak. The student did a PRU speak driver, but he didn't he didn't integrate in with our main kernel. So I just needed a little bit of help there. So you'll see this PRU speak.c and PRU rproc. Those are the two main source files that implement the kernel driver. There's also this one called external glue. And an external glue just kind of provides the interface between those two. If you've never seen a kernel driver before, this might be a little worrisome. Might seem a little complex to you. But most of the magic happens through this thing called a down call. So the remote proc driver that we're using here implements this thing called a down call that provides us a mechanism for sending.
remote proc driver?
Yeah.
Okay.
So this is the PRU RPROC. That's the remote proc driver. So the remote proc driver, this is a big chunk of code that gives the mechanism for loading the firmware and providing shared memory buffers for communicating between them. But there's just a couple of interfaces that I'm leveraging. This code is long. I don't necessarily want to spend a lot of time going through RPROC itself, but I wanted to show how to use RPROC. Because RPROC, this version is some 3,000 lines of code. But PRU-Speak is a much smaller, much more manageable 500 lines of code. And what it does is it leverages down call and it leverages shared memory. Right, so this data structure is where is kind of provides all the different mechanisms. This MISC device interface, that provides files back to Userspace. So that's how I talk to the Python script, right? So it's using MISC device to set up a miscellaneous device driver, and we'll create a bunch of different sysfs entries against that miscellaneous device driver that provide you mechanisms for calling different functions on the board. Down call is coming from the remote proc driver. So I get a function pointer here from remote proc, and that gives me a mechanism to talk from the driver down to the PRU itself. So when I call down call, it's actually sending an interrupt down to the board. As I said, it's not really interrupts. But there's a standard set of firmware in my PRU code that is looking for the flag that says that there's a message and a certain data structure to say that I've got some data, and it just provides me a mechanism. So there's an integer that says what the down call is, and it can take 5 different 32-bit arguments.
So that's the communication between the file system, the programming system, and the CPU and the PRU.
Specifically, this is the interface between the PRU-Speak driver and the PRU, the firmware running on the PRU.
So this is not PRU-Speak, this is the CPU?
This is running on the main CPU.
Right.
That's the Linux kernel driver.
Yeah.
It's the PRU-Speak driver. It's the thing when you type mod probe, PRU_speak, this is the driver that gets loaded into the kernel. And okay, let me start with this first one. You see that structure of MISC devices? That structure is what defines sys, MISC, no, sys devices, MISC. Maybe it's bus MISC. MISC. What is it? Sys class MISC. That's what it is. So if you see, right under sys class MISC, right, there's PRU-Speak. So this PRU-Speak is a miscellaneous device driver, right? And through that, I'm creating different sysfs entries that give me different operations, right? There's an abort operation, there's an execute operation, there's a single command operation, there's this status operation. And so with Linux makes everything into a file, right? So these are the different file interfaces that are exposed. So the Python layer is taking that textual information and putting it into a essentially something that can go into that, like it's taking it into making a collection of 32-bit bytes that get placed as arguments into that down call. So each one of these different interfaces corresponds to a particular down call. So these are each different messages that I can send down to the PRU that take an array of 5 different 32-bit words. Yeah, up to 5 32-bit words. I mean, you don't have to use every parameter, but that's what gets passed. And so that Python code is tokenizing the text into 32-bit words, and then you send those 32-bit words down. In the future, I'm going to add to the drive. I'm going to put that code into the driver itself, so it provides another file entry that is actually just the just go straight to interpretation and move that down to the kernel. But right now it's being done in Python.
Okay, so that code that you showed us is the kernel code to send stuff from the file to the
Right.
firmware.
Right. This
from
is
PRU.
exactly to the
PRU's got some firmware running in it anyway.
that answers these down calls. And you'll see like here, there's the debug function, right? So this is essentially the function that gets called when you read and write that debug file from the Userspace, and so it's doing this down call, and and it's providing those different addresses. So this is where it actually sends something to the PRU, and there's one of these for each of the different interfaces: debug, init, execute, abort, status, and they're not doing too much here. They're just essentially just grouping stuff up and sending it on down. And this is where I register those interfaces with the kernel. So this is a standard macro for the kernel interfaces for your creating a device driver, and this is the name of the I don't know if that's the name of the interface or the function, but then there's permissions, whether or not you can read and write to it. So there's different options of the interface back to the kernel. You can look this up in any sort of resource on the kernel device driver, right?
Any type of priority in that?
No priority in there. These two functions, load and reset, I'm leveraging off of the main remote proc driver. So those are already those are written already as part of the remote proc driver. And the student wrote all these functions, but I just
Yeah. Are you filling with firmware in fashion, or using that all just kernel?
well, the firmware, yeah, I mean, there's custom firmware for PRUs for the PRUs themselves. So I wanted to show the kernel first.
Okay.
This is the kernel interface. I'd show the main interfaces that we're using here from the remote proc driver. That down call, and then there's a handful here. If I look at glue, I'll try to find out where it is. So this is where the shared memory allocation is done in the probe. So when the driver is loaded, we have to allocate the shared memory for doing the communication. And so we just have to use this kernel coherent DMA allocation interface for allocating the shared memory. So that's being used in two places. It's being used for, like, the down calls give me the ability to initiate commands down on the PRU, but I still need a way to get data back. So there's shared memory being used through the return values. Also, when I load when I start a script, I'm not just providing a, it's not just coming in these 32-bit values, right? It's coming with a whole chunk of memory. So I'm using the shared memory for, that's code. So I say I, but I really should mean Deepak. So SHM_code is what's used for the script memory. And then SHM return is used for the return values.
Is there any kind of semaphore or something
The is valid flag, I think, actually, no, that's just to say whether or not the memory is allocated or not. I'm not exactly sure how he's implementing, if he's implementing any semaphores here. I mean, you got shared memory, so you can do, you can create your own mutexes or semaphores.
Especially if you want to read it,
Yeah.
you want to end up basically figuring out what the hardware, which system the hardware is. If you place two bytes to the same memory cell, the hardware might be configured with just one over, 1 hour to win, and semaphores are a way to fix that. So software than hardware, right?
Absolutely.
And I was just wondering if there's anything like that in there. Because it's really a hard problem to deal with the software.
If we look at what he's got as his kernel interface,
Down through all the code?
I have not gone through all the code exhaustively, no. Yeah, so he's open to, yeah, that's why I can't answer it, because I haven't gone through it exhaustively. I've only gone through the stuff I need to do to integrate with the 3.8 kernel. Yeah, so this is where he's directly mapping that the bytecode. So if you see code SHM, that's the shared memory. But I don't see, here I don't semaphore.
That stuff might do it, because I mean, in the end, that's how, a disk controller gets space memory and writes stuff out to the hard disk, right? It's all based on DNA and that kind of stuff. So if he's just using the standard kernel routines that do that,
He's not. No, he's going right around it. And actually now I remember part of this, right? So to look at whether or not the return value is valid, he's using, so he maps it into memory and he's looking at a counter. So when the counter increments, he knows he has a new value within the return. So that's not a good semaphore. He should use a better semaphore mechanism than that. But essentially he's counting on, if he looks at this memory value updating and it's incremented, he knows that the other portion of memory is valid.
Right. In the past, we had
not too bad.
Same problem, but we ended up looking at that counter. We were trying to resolve. We ended up looking at that counter too frequently, and then we went to the other side from right next to the value.
Right.
Right. So because you're really dependent on the cycle times and how fast something can do memory access and all that kind of stuff. You
can't. At least from the A8 side, you can't read and write fast enough to block the PRU from accessing it.
Okay.
The question is, could you do it fast enough on the PRU side to block it? I don't think so, but I don't know what the memory interface priority encoding looks like. Yeah, I mean those are all perfectly valid concerns.
Well, actually, I was asking James, you sound like obviously the stuff works, right? So whatever software implementation has deals with that.
Well, how many people are actually using the PRU speak?
Not that many. It's not really worth testing.
Production type.
No, this is pretty brand new stuff. You don't know if there's not any leaking issues in here. But this is intended really for right now as just kind of a reference to help get you started. Not as a definitive production. But I know with the Beagle Logic stuff, it's also using this remote stuff. I mean, that's working pretty darn well. Getting us to 200 megabytes per second. So I mean, that one's kind of beaten. So you can do set I, comma. Like here's some example stuff you can type. The set DIO4, DIO capital DIO, and square brace open 4. Comma 1, comma 1 enter. You should see the LED turn on if you've loaded everything properly. Is your LED oriented the right way?
That might be a different.
I mean, 9 times out of 10, right? Let's see. Try not to put it work. Why is it so low?
Lighting the thing up?
Yeah.
There you go.
Maybe somebody burned it out. I don't know. So let's look at the firmware.
Oh, there it is. Not quite connected.
Oh, was that it? It came on?
Yeah, it's coming on.
Actually, let's look at the down call first. Here's the basic interface for the down call. So this is, if you want to use this remote proc driver, you need to have this portion implemented as on the PRU. So it's looking at these And actually, I've not looked at this to any real extent to kind of know how it's implemented. I just know that this is kind of the standard interface that he's provided here. So you need to call this in your loop to wait for the down calls. And then you can implement and see the actual down calls, right? So this is the event loop. So it's macro to look for the event, clear the system event, and then do the ST down call. So that calls that chunk of assembly. And handle down call should be probably an array, I believe. I don't know if it's a function. Okay, it's a function with a. So you'll get called back with an ID here. So remember those 5 different arguments that we were calling from the kernel device driver. So now we're getting called those. So one for the ID, and then we actually get those 5 32-bit values. So this is our remote procedure call mechanism. Yeah. And you'll see one of these functions implemented for each one of the different mechanisms, right? So there's debug, init, exec, abort, stat. These individual instructions. All right. So if I want to run a 32-bit instruction or a 64-bit instruction, that's how the individual instructions are run. And then exec will set the is executing flag. And if executing flag is set, then in the event loop, back up here to the top of the main event loop. Where's the event loop? That's where we started. Okay, check event. Is the while one? There we go. There's the while one. So the while one calls the check event, and if the flag is executing is set, so we're saying that's essentially when you set run, the script is running. It just continuously calls execute instruction. So it's going to check for new events, like new messages coming from the ARM between executing each one of these instructions. And so my thinking is that this provides enough of a framework for people to try to build off richer systems. Like you just, your individual functions that you might want to be able to run on the PRU, as execution, as instructions within this sort of an interpreter environment. And then you just kind of run them in a loop, and in between you can check for commands that allow you to continue to communicate between the A8 and the PRU. So I'm hopeful this gives people a real framework that they can go and build on top of, and also we'll have enough sort of a standard implemented library that we can do to talk, how do you do pulse width modulation, how do you do reading from the A to D converters, how do you do the different digital I/O, that you can use all those library functions to kind of expand this firmware to do whatever it is you need. And this is all compiled. I installed the TI compiler. I don't know if I have the firmware installed here, but it's under opt PRU.
What was the line that installed the firmware?
The install of the firmware is the make file that's in here. You look at this make file.
So the firmware's already.
I'm sorry, that's the wrong one.
Preloaded on the board.
It's preloaded.
Is it preloaded as part of the build or preloaded on the board?
It's preloaded as part of this magical card.
Okay.
Otherwise, what you need to do is download it from the PRU speak and do the make file. But you'll need to install the TI-C compiler, which gives you this shell script installer. So if you look for if you download the compiler, it makes you, In the future, we will ship with the C compiler on it. In fact, I'm supposed to be getting it within a month so that I can actually ship with the TIC compiler on it. Ideally, I'd have both the TIC compiler and the GCC compiler. Who wrote it? GCC is open source.
Right, what additional features? You said you need to use the TI.
Oh no, I don't know that you need to use the TIC compiler. It just happens to be that I used it. But yeah, I just haven't tried the GCC. If I find the GCC works well, the thing that I want to ship with the TIC compiler is I expect it to provide a certain degree of optimization and testing across a lot of different things that maybe the GCC compiler wouldn't. You know, so different code would probably run better with one or the other. Like if you're pulling open source packages from a lot of places, GCC would probably be the better compiler for a lot of it. If you're pulling the TI example code and other stuff that's specifically targeting the PRU, the TI PRU-C compiler is probably going to be better. Yeah, yeah. I've been talking to the Tiny G folks about porting their control system stuff to it, and theirs is in, apparently it's in C++. Yeah. Yeah, as long as it doesn't use STL. So here, there's if you see the TI downloads, there's an A8 download for the PRU, so that actually runs on the BeagleBone itself, and it makes you log in. So you have to have a TI ID. Anybody can get one, but they use this for export control. They're getting rid of this. They're about to release a version that's freely redistributable, and I'm told before the end of October. Oh my goodness, they really have to. So I don't want other people to have to deal with this. My company, Texas Instruments. How about that as a company? Afghanistan.
Afghanistan, I think they've opened up the door.
And I'm pretty sure this is going to be used for military. I guarantee I'm not going to use it to create missiles.
We're not gonna do it. You're giving us that code here.
But what you end up downloading is this shell script. It's .sh file, and which again has another click wrap. Once you get it installed, it looks like it expands in the root directory, but I just moved it into opt. There's a couple of magic parameters to be able to use it, and by that I mean you need to put it in the path. You put it in /opt here. You know, so it's not in the path by default, so you need to do export path equal $ path. Hopefully you guys know mostly how to do this. But opt PRU bin. So you have to put the bin in the path. And then you also need to set these variables called dir and cdir to, of course, GCC uses totally different ones. But that's that's how it finds the libraries. That's how it finds the runtime support libraries when it actually wants to link. Yep. And it looks like I didn't provide the firmware here to actually show a build. Well, that's not very useful, is it? But at this point, I would just be able to type make here using this make file, right? And it uses the TI. Let me show you the commands in the make file. All right, so it uses the CL PRU to perform the compilation, and then the LNK PRU to perform the linking. And you also need this linker command file. So I recommend just copying one. But this gives you the memory, it explains the memory map to the linker. So things get hard linked to certain physical addresses. So you need to provide that to the linker. Also setting up different regions for register maps, for peripheral register maps.
So PRU code is basically wrong with the code. Load specific address and environment specific address. It doesn't have any backup in there.
Yeah.
Or binary format.
Yeah, it gets stored in ELF.
Okay.
So if you parse it, right, it shows you that it is an ELF with symbols, right? So you can right. So you can actually look at the symbol. You can actually look at the symbol table in the ELF file, because it's just an ELF file. And if you use the other firmware, if you use the instead of using the remote proc, if you use the UIO PRU-ICSS, then you need to have a parser that actually parses it and then loads it into chunks of memory. Whereas the kernel driver understands how to parse ELF, right? Linux understands how to parse ELF binaries and just load them into do the fix-ups and load it into the fixed memory addresses. And I don't think there actually are any real fix-ups, because I don't think this is really relocatable code.
Well, I figured because you provided the linker table there, right? The linker's going to do that.
Yeah, but I mean, just the linker may provide symbols to still be resolved at runtime, but I forget what NM tells you. Like NM tells you, I think, what symbols are actually still need to be resolved, but I don't think that any symbols need to be resolved at load time.
Since you provide, you should have the firmware, right? It's kind of like if the use operating system has millions of calls.
Yeah, there's no
Basically, just a basic piece of code that's running on the PRU.
Exactly. So yeah, this is your whole firmware right here. Firmware PRU0 firmware. Then it also links in the syscall. This is the disassembly, right? So when you build it, you can look at the annotated this looks like the I don't know if you ran the disassembler or if you ran the because you can have the C generate annotated C, the C compiler. So it'll actually produce an assembly listing that's annotated with the C code itself that generated it. So you can look. This is the actual PRU assembly code. Yeah, that's the machine code right there. The offset byte, the machine code, and then the mnemonic. And you see the PRU assembly isn't too bad. I don't know exactly what LBBO means, but well, LSL is left shift left, right? So you have and. I'm sure that's some sort of store operation. That's some sort of load operation, but it's like doing some selective loads. Q, that's branch not equal. But Q, I don't. So that's some sort of that's a decision.
Load byte first.
Right. So you can actually load a series. So you can actually load. It's probably loading 4 bytes at a time, right? Through the 4. And you can load registers, like because you can load. So that may just be loading a single register, but you can actually load like a series of like 4 registers from memory, one after another. So it'll automatically increment if you. So you can fill your register array with an array for memory. It's a pretty nice little assembly language.
On that load library, you can do two ways, like you said. You can load registers, right? And you do an account of how many registers to load.
Right.
You can use zero, but when you see a user account.
Oh, will it?
You tell it to not load zero registers.
It won't just do a no-op?
No. It's that, it's the PI that processes stuff. You should get PI that counts.
Well, then I would advise not doing that.
I can understand the pain of the guy that wrote the microcode, You want to put in an extra check for that, or do you?
I don't see why. I mean, yeah,
Right.
But you needed an extra halt instruction, which it has a halt. All right. Sorry, the boss checking in. So, we've gone probably way over. We're half an hour over. How is this? So what can I do to do this again and get more out of it? So I have some code that shows the to try to do the LCD, but just doing this from the PRU speak. But I had an issue with the AND instruction, so I was just trying to do here. I was trying to do comparisons of bits in order to decide whether or not to shift to high or low.
Yeah, you're right.
And this operation's not working right now. It's always saying that this AND is always returning true.
So, okay.
So it's always shifting out high bits.
So what you did today was you showed us how to get things sort of loaded up and one instruction running, but my purposes were the 0 and 1.
Same goodness.
Yeah,
Wait.
0 and 1.
Well, you're just like, oh yeah, it's PRU. You're controlling the 5-volt valve.
So okay.
I don't know which way is which.
Doesn't matter. So what you did was you everything wasn't completely set up, which is okay. You showed us how to do a couple little steps, and then for the most part, you showed us how all the pieces fit together. You went out and looked at everything, and showed us where all the different pieces were. So since this was sort of like a tutorial, you could potentially send us this code, since some of us, I took some notes. I could send the notes to people if they want, and of all the additional steps you might be able to remember. Just here's the build. You could load this specific build up.
Yeah, I could give this specific build out the.
You could
Sure, that's
load it somewhere.
Sure, that stupid TIC compiler. Maybe I shouldn't have dropped that on there.
So you show the instructions that you went through, and then you can also that little program that you wanted to run. Well, on these on this thing. So that code's already on the image, but you need some instructions of how to run that code.
Well, it doesn't. The AND instruction right now, it won't run.
Right, but once you get it working, you could post it, tell us how to run it on top of the additional instructions you have. And for those of us who've gotten these, obviously we need to know which pins to stick these into. So that too. So we can do this as sort of like a homework assignment. So that's sort of like.
Well, is there a good email thread that we can all follow on? I don't know if it's Meetup. Okay. Okay, well, everybody's signed up on the Meetup, right? All right, we'll follow up on the Meetup, and then
for those who want to do it, still have more, right?
Yeah. If you want the,
some of that 3 too.
Yeah,
I've got several more of these little the LCD displays.
I was thinking that either a handout or a text file would be access, so that if we fall behind on the, for me, I was able to got my idea of it. So it'd be nice to be able to follow through and without
Put that either on the meetup.
It's a nice tutorial.
Right. Well, if you're doing a class, you could have to escape it, have
Or have it as part of the text file, so you got that.
Yeah.
file, so you got it.
So maybe I can put that text. So why don't I clean up the image a little bit based on some of the feedback here? Maybe fix the bug. Yeah, get with a firmware source.
Instructions. Don't vary too much from what you've already done here, because you saw that. So
Right.
Sort of have an idea, and it's good for us as people who are trying to learn it to do some of the steps. So, you know.
I won't fix it up so that it automatically runs. I'll make sure you still have to do a couple of
What the
commands.
steps are, and you sort of understand what they are.
But include the text file. Maybe you can give me the first draft of the text file,
Sure,
and I'll clean it up and correct it. And then I'll post it up on S3 and so that everybody can download it from the.
Dash history helps too, and that tells us
Yes.
yes.
Yeah. Actually, let me save my history out right now.
I use that several times.
That was part of the tutorial too.
Like, remember what I was doing before I prepped my history?
So I don't know what to do with this. This doesn't seem to work.
Yeah, I don't know. It's yeah, I just switched LEDs, and so it wasn't the LED.
It's not the LED.
So record everything that you do.
So I don't know. We can hang around and debug yours a little bit, but I think any other kind of feedback as to how to make this better? What did you not get out of it? What did
I think it was really good. I mean, I had not done anything with BeagleBone other than having one to browse a little bit. But it answered a lot of my sort of really deep technical questions on like what the PRU is. The next thing that I would do, and that's just me, is I would try to figure out how to do, like what you said, access techniques or something. Because like my goal is getting some sort of fit loop or whatever on, and I would need analog input, right? But that's, not to say that what you presented here wasn't enough. It was more than enough. I think it was a really good overview of what you can do and how to do it, right? So there wasn't any gaps in something like how it goes from the BeagleBone to the BeagleBone to the fixed.
Perfect. So I'll just continue to just get better at delivering this.
But he's gonna make it. You might want to space for that. But yeah, I mean, we insert your, yeah. If you want, what you're running on, you just like insert that disk and like DD from.
Yeah, if you just DD from the
SD0 to
SD.
SD1.
Yeah, if you want an exact copy of that, we can do that.
No, not at this.
All right. All right. Thank you very much. And there's still more food, I think, as well. Thank you very much.
Thank you very much.
I should have left it for the thank you all.
You want to thank the host?
This is definitely a lot nicer than trying to do this at I3. Way too loud. Processors.wiki.com.
Weren't they gonna get that annex?
Okay.
Or did you already go to get
They did the annex, but like a lot of people didn't like it because it was so separate.
Right.
But
Try it again.
that was before
You don't
my
think I
time.
should say
Right
this?
now, I'm like, can we get that annex again? Because I would love to just like
You gotta do it
get
again.
away. Sometimes I stay home because.
You need me to sign
Yeah.
the
So how do I shut this off and hold that?
Oh, I'm just
Shut
on
down.
YouTube, so.
Oh, actually,
Or actually, I don't know. I'll give it a video.
which one? PowerBound's closest to the Ethernet port, right?
Oh, what's it called?
PowerBound's closest to Ethernet, right? Yeah.
Definitely.
I get PowerBound to reset confused sometimes.
Yeah. I don't know.
Well, that seemed to work. That was this one?
No. That's reset. The inner one is.
The inner one is
Okay.
You want to copy the
So it's down.
Am I supposed to press
On
on
platform.
Or you're having me upload them.
power button?
I would rather you upload them to YouTube.
good.
Oh, I didn't stop the
Video.
from. So this has been recording the whole time.
Okay, so at least they have thank you to Hello World.
This one here.
Yeah, thank you, Hello World, and good night.